Markov models, the actual state of the system becomes hidden and is only accessible through the so-called emission probabilities. At the top of this figure are events organized as a Markov chain and represented by the random variable x, whose states vary through time. And we have represented a number of time steps here. In a hidden Markov model, the state of the variable x will not be visible. What is visible is a state of random variable v, the visible variable, which will emit its states with a certain probabilities. Hidden Markov models are used to learn coupling between two streams. In rational prime solving, they are used quite a lot because when you collect information from a sensor, often what you want is to infer a state that corresponds to what the sensors are portraying. For example, you may have many weather sensors and weather stations and use a hidden Markov model to try to discover what the actual state of the weather is given the emissions of the sensors at various times. We use a graphical model really similar to the one drawn here for that. Other popular applications of hidden Markov models, or HMM, is in speech recognition, where the visible stream is the audio signal and the hidden information are the words pronounced. Likewise, they are commonly used for movement or gesture recognition. In computational creativity, there are also applications where there is a coupling between two streams that evolve in parallel and in sequence. In music, HMM have been applied to accompaniment or harmonization on a given melody or in a given style, or to learn the articulation between composition and interpretation. The three algorithms that are available and applicable to hidden Markov models are the forward algorithm, which computes the probability that a particular sequence occurred, assuming that we know the transitions and observation probabilities, as well as the initial state. The Bohm-Welch algorithm, which is applied to find the most likely parameters on the basis of observed sequences. And finally, the Viterbi algorithm, which calculates the most likely sequence of hidden states called the Viterbi path on the basis of the observable sequence. This is the one that is usually used when generating new sequences. Hidden Markov models applications in art and computational creativity stay modest, likely due to the fact that these algorithms are not straightforward. However, and as mentioned, a number of musical tasks and mappings have been explored. In jazz, Hirzel and Sokop in 2000 trained a HMM with chord progressions being the observable signal and the melody being the hidden signal. Hidden Markov models have also been used to generate a counterpoint accompaniment to a melody. The system is given the melody as observable events, and it predicts the counterpoint as a set of hidden states, which is pretty much the reverse of the previous architecture. In conclusion, hidden Markov models have been applied to all sorts of recognition and classification problems, and they can also be used for generation, mostly by exploiting the Viterbi algorithm. The advantages are that they are one of the most efficient and popular ways to learn and generate discrete sequences. In addition, unlike Markov models, hidden Markov models do not only capture horizontal sequential dependencies, but also allow modeling some of the vertical dependencies. Hidden Markov models are also better at respecting structure than regular Markov models. However, there are also some drawbacks of hidden Markov models, namely that they require a good understanding of the domain or task to fine-tune the model architecture, and they also require a rather large training set to achieve good performance.